Welcome to section 5.5. In section 5.5, you're going to take a look at an integration technique. So a way to do integrals. Now that could be either the definite or indefinite. Okay, because this is the technique not about finding the end value, but it's a technique that we're going to use to find that antiderivative. And this is an integration technique. It's called substitution. So basically what we're going to do in this section is we're going to take a look at how to recognize and then how to deal with, how to integrate, how to find that antiderivative when our integrand is the result of the chain rule. Do you remember the chain rule? The chain rule said that when you take the derivative of a composite function f of g of x, that it was going to be f prime of g multiplied by g prime of x, that business. Okay, so going that way was differentiation, and going this way is taking an antiderivative, which we now call integration. And so our job in this section is to look at this piece and be able to recognize the results of someone doing the chain rule, that our integrand is the chain rule, and then undo that. So our objectives are to use that pattern recognition skill to be able to look at something and see it as that f prime g times g prime to find an indefinite integral. And then we're going to use what's called a change of variables. And that's why it has the name substitution. Because what we're going to do is we're going to do a substitution of variables, a change of variables. And then once we do that substitution, we'll then use just plain old integration techniques to find that indefinite integral. And we'll also use that change of variables to find the value of a definite integral. So once we get to these two steps right here, these two objectives, it's the next step, the next thing that we do is going to depend on what kind of integral we started with. Was it an indefinite integral or was it a definite integral? Right? And then for some reason, I don't know why, but this is really common, they put these ideas of even and odd functions at the end of these section. It has nothing to do with what we're doing in this section, but it's like, oh, hey, I got to put this somewhere, so put it here. Okay, it doesn't really make much sense. All right, so that pattern recognition thing that I was talking about. And so because we're taking a look at a technique for integrating composite functions, what we need to do is we need to be able to look at and see things as composite functions. For example, if this was given to you, nothing that we've been given so far in terms of a technique for integration will help us with this. None of our power rules, none of our trig rules, nothing will help us solve this. So what we need to be able to do is to look at this and recognize that that is two things that are being multiplied together. Because remember, the end result of the chain rule is two things multiplied together, and that one of them appears to be the derivative of the inside part of the composite function that is the other multiplier. Okay? The technique that we're going to use requires two steps. Okay? The first step is to recognize that we do have one piece, one of our things that are being multiplied together, one of our multiplicands, if you want to get fancy about it, is a composition. And how we're going to deal with that. So one is composite, the other is not composite. And then we're going to use a change of variables, that's what we call substitution, to make it work. Okay. Now that second step is really, really commonly called use substitution. In fact, you will sometimes see this called not substitution, but use substitution, because it is incredibly common. And when I say incredibly common, I mean just about everybody who teaches this and everybody who wrote a book on this and everybody who does this for whatever reason, and I don't know why, when we change the variables, we change the variables from whatever was given to us into the variable u. Why u? I don't know, but u seems to be this variable that we use a lot. If you think back to our derivatives, when we wrote the chain rule variant of our derivatives, we often replaced the x's with u's to represent some function. It just is something that happened in calculus, and where it began, I don't know, but it's the thing that we do. Okay? All right, so here's the first step. The first step in being able to do u substitution is to remember the chain rule for derivatives. Okay? So the derivative with respect to x of f of g of x. So there's an inner function and there's an outer function. And when we took that derivative, we got the derivative of the outer function of the inner, and then multiply that by the derivative of the inner function. Now what's really, really important here is this right here. That the result of this derivative technique, the chain rule, was that the derivative had two pieces that were multiplied together, where one of those pieces, this g prime, is the derivative not of the whole thing, but just the derivative of the inside of the composite function. Okay? And if that chain rule is true, if moving from left to right here is taking a derivative, then going backwards, that is taking an indefinite integral of our f prime g, g prime, must take us back to the original f of g of x. And of course, what's this doing here? Well, whenever we do an indefinite integration, we stick on that plus c to say, hey, this is not the only answer. This is just one of a family of solutions. And that family of solutions, of course, is just vertical translations of each other. Okay? All right, so that's what we're going to do. We're going to somehow look at this, use pattern recognition to say, hey, there's two things being multiplied together. One of those two things looks like the derivative of the inside of the other thing. I think substitution will work, and then we'll try substitution and see if it does work. Now remember, just because we are in the section on substitution does not mean that everything is substitution. But I will say this. If you talk to any student who's gone through Calc, not just Calc 1, but Calc 2 and Calc 3 and beyond, they will tell you that substitution, by far, is one of the most common integration techniques that we use. Okay? Composite functions are everywhere, and because composite functions are everywhere, we're taking derivatives of them and we're taking antiderivatives of them. We're integrating them and we're differentiating them. So if you think back to when we were taking derivatives, once we learned the chain rule, do you remember how common it was to use this chain rule right here? It was like every other problem was, oh, there's a chain rule in there. Oh, there's a chain rule in there. Because it's just really common in math to have composite functions. And if it's really common in math to have composite functions, then we're taking derivatives and we're taking antiderivatives. We're differentiating and integrating composite functions all the time. Right? All right, so here's how we're going to do it. This is our Theorem 513, the anti-differentiation of a composite function. Starts out with the required definitions. So let g be a function, let f be a function. If your integrand looks like this, the answer is this. Wait, what? I don't understand what they're saying here. Why are they saying what they're saying? Okay. Because I thought that this right here was supposed to be f prime. Well, here's the problem. If I'm taking derivatives, then of course it's going to show up as f prime over here. But if I'm just handed something, there's never going to be that prime symbol there in my integrand. I'm just going to have some function, f of g. And so if I'm taking an antiderivative, if this piece right here is supposed to represent f prime in our definition, then when I take its antiderivative, that's why that big F shows up. Okay? And so what we are going to do in the u substitution part of this is we are going to make these two substitutions right here. We are going to say that we are going to replace the entire function g of x with just simply the letter u. So this g right here turns into that u right there. And we are going to replace the entire term g prime dx with the expression du, which gives us that right there. And now we have an integral that says the integral of little f of u du is equal to big F, because what's the relationship between little f's and big F's? Well, big F is the antiderivative of little f, right? So I know this is a lot to process right away, but basically we're looking at outside functions and inside functions, and my job is to be able to recognize that two things are being multiplied together. One of them is the derivative of the inside of the other. Right? So there's an outside function f, an inside function g, and we're multiplied by the derivative of the inside function. All right. So these guidelines right here, we'll come back and take a look at those as we work this, but let's just take a look at this example right here. All right, so I have an integral. My integral is the quantity x squared plus 1 squared multiplied by 2x dx. So for clarity, I'm just going to highlight that multiplication. And now I'm going to say, look, we have two things being multiplied together here. Okay? One of them is composition. Okay? And so what is the inside part of the composition? Well, the inside part of that composition is x squared plus 1. And if you took the derivative of the inside part of that composition, you would get 2x, which is the other part of our integrand. So I have laying here in front of me on the screen, I have two things multiplied together. One of them is composite. The other one is the derivative of the inside of the composition, which means that this is perfect for a u substitution. Okay? So let's take a look at those steps. The first step is, once you have identified that you are going to use u substitution, is to choose the proper substitution for u, to write u as g of x. Okay? G of x, remember, g of x is the inside. So we are saying then that u is going to be the same as x squared plus 1. That u is x squared plus 1, which sounds grammatically incorrect, but is correct. Okay? Now that we've identified u, we are going to compute the differential du. Okay? So we are going to differentiate this with respect to the variable of the integral, which is x, so d dx. Left-hand side gives me du dx is equal to 2x, and then I'm going to do that thing that I did in the differential section, where I'm going to multiply both sides by the differential dx, and that's going to give me du is equal to 2x dx. Okay? At this point, I have done step 1, I have done step 2, I've computed the differential du. Now I'm going to do step 3. Now, I don't really care for how the book wrote step 3. I would have preferred to write this and say, do the substitutions. So now I'm going to do the substitutions. And so this integral here is now going to become the indefinite integral of u squared du. I'll give you a second to catch up to me. Remember, we call this inside piece u. And so that's why there's a u squared sitting here. In our calculations, our scratch work over here to the side, we identify that du is the same thing, is equal to the entire expression 2x dx. So this whole piece right here just turns into du. You should notice that this squared never was substituted out, never was dealt with, never was changed, so still exists down here in our new integral. Right? So now that I've got the substitution done, now that I've done what they're calling step 3, I'm going to do step 4, which basically just says, do this integration. Right? The integral of u squared du is going to be 1/3 u cubed plus c. Right? I am not done yet, though. Here's the challenge. Here's the problem. The original integral, and I'm going to have to erase some of this so we can actually see that original integral because I wrote a lot over it. Right? The original integral was delivered to us with the variable being, why won't you erase? Huh, weird. With the variable being x. So then my final answer also has to be in the variable x. So at this point, this is incorrect to have a u there. So now I'm going to have to do another substitution, or as sometimes referred to, I'm going to have to do a back substitution and replace u with what u represents in terms of the variable x. So now down here, the final step, the 1/3 is still there. U becomes the x squared plus 1 from our substitution statement. The cubed is still there, and the plus c is there. Right? Now, if I was in the least bit concerned about the accuracy of my result, I could just take the derivative of this whole thing right here. I could just take the derivative with respect to the variable x, and I would get that original statement up there of u squared plus 1 squared times 2x dx. Okay? So we did replacing u to obtain an antiderivative, and then the last one is if you feel the need to, check your answer by differentiating. Right? That's 16 minutes right there, so I'm going to stop this video and make a second one where we'll just do a whole bunch of examples of substitution.